Hello and welcome to the second video on the Boolean logic, Boolean algebra and circuits playlist. In this video we are going to explore the importance of being able to reduce a Boolean expression to a simpler form, and then very briefly we're going to touch on the implications of that for real-world digital circuit manufacture. So the purpose of this video really is a precursor before we jump into the heady world of Boolean algebra and Carnot maps, just to talk very briefly about why it is that we actually need to bother taking a Boolean expression and seeing if we can simplify it into a simpler form. So to demonstrate this further, let's take a simple Boolean expression, some Boolean logic, where Q is logically equivalent to A or B, and then to that we apply an AND logic to the result of A or C. Well, it doesn't look particularly inspiring as it is on the slide. One of the ways that we can bring Boolean logic to life a little bit more is to illustrate the expression in the form of logic gates and a circuit, of course, which is what we're going to do now. So we're going to take a little bit of time just to explore the circuit to make sure that it does actually map logically with the expression that we've got at the top. And while I was doing this slide, I just thought I'd pick up on something which is really important. It's just a related aside, which is to say, please note the way in which we draw circuit lines which are not joined together but which overlap. This is really, really important, because if you forget to put the little bump in there, if you're drawing a circuit like this in your exam, then essentially your circuit is incorrect, because it will look like A and B are joined. That circuit wouldn't work at all. But there are circuits where you do want to take feeders off a particular input. So if these are separate like they are here, A and B, you need to make sure that if your lines cross each other, you put the little bump in accordingly. Okay, so let's see if these two are equivalent. We'll start off with the logic that's applied with the OR gate here. We've got A and C, both of those are inputs to an OR gate, so the way that we express our output from our OR gate is A or C, and you can see that we have that here. Now in this particular case we've got brackets around the A or C, and we do that in a similar way that we require to put brackets around expressions in maths for bid maths, to make sure that if we need terms in a bracket to be evaluated first, then that is the case if we put brackets around them. And what we're basically saying here is, before we get any further in our circuit, we must have A or C evaluated first. In other words, what goes into the AND gate with B must be A, and then logically with C before we go any further in our circuit. Okay, so let's move further to the right hand side of our circuit. Here we have an AND gate where we are applying AND logic to B, and then the result of A or C as inputs. The result of that is the expression here, B AND, logically ANDed with A or C, and we can see that's represented in the expression here. And because it's a relatively simple circuit, we only have one more consideration with A. So our expression is saying that the result of this in our circuit, B and A or C, then has a OR logic applied to it along with A, and that's what happens here. We have A as one input, and then we have B and A or C as our other input. That of course gives us our final expression. Our final output from our gate is our final version of our expression here, which is A or B and A or C. Okay, so that's a simple Boolean expression that's been illustrated as a logic gate, and we can take the time out to see that those two are in fact the same. Now it just so happens that A or B and A or C is logically equivalent to A or B and C. These two expressions are exactly the same. You can see that the one on the right hand side is a simpler form. How do I get from this expression here to the one on the right hand side? Well, that's something we're going to tackle in the classroom and in future videos, where we are going to apply the rules of Boolean algebra so that we can tackle something like this and indeed find that this expression on the left can be simplified to one on the right. That's for another time. However, I did just want to point out that these two expressions are logically equivalent. What that means is that if we illustrated these with logic gates and actually created a circuit, if we applied the same inputs, the inputs of A, B and C, to both of our circuits, we would actually get exactly the same outputs. One of the questions you're probably wondering is, why do we actually need to bother simplifying Boolean expressions in the first place? That will become apparent very soon. So let's have a look at what our two equivalent circuits look like if we chose to illustrate our equivalent expressions with circuits. There's the one that you've already seen on the left hand side, and here is the one on the right hand side, which is the circuit for our simpler version. A or B and C. Let's trace it through again. We've got B and C there, which is expressed here, and of course our final output is the result of taking A and A with B and C. It does get a bit of a mouthful sometimes, and then applying a logical OR to those two, and then that gives us our final expression. There's our final OR gate, which takes B and C, and then we apply an OR logic to that along with the A as our two inputs. So our logic gates map up with that expression as well. Okay, so what we could do actually to prove that it is the case that these two are equivalent, we could actually simulate our two circuits using logic.aly, just to make sure that they are indeed giving us the same output if we apply the same inputs. So I'm going to take a break from the slides. I'm going to pop up logic.aly, where I've done these two circuits, and then we're going to tinker around and see if we get the same results on both circuits. Okay, so let's see if our two circuits are logically equivalent in logic.aly. So if you've not used logic.aly before, essentially in our initial states here, both of our circuits are equivalent because we have 0 on the output, and we know that because both of our lights are off. In logic.aly, whenever we have a 1 registered in any part of our circuit, both the circuit lines and the lamp will glow as blue if it registers a 1. So what we'll do is we'll ignore A to start with, and we'll just tinker around with B and C. So let's switch B on both of our circuits, and you can see that our two circuits are equivalent. We only have a 1 flowing through this part of our circuit here. Let's switch off B and switch on C. Okay, oops. There we go. So both of our circuits are equivalent when A is 0, B is 0 and C is 1. Let's switch on B for both, and you can see that we get a blue glowing lamp, which means we have a 1 on the output in both circuits. Let's switch on A for both, and you can see that our two circuits are equivalent again. Let's switch off B on both, and you can see we have equivalence. Let's switch off C on both, and you can see that they are equivalent. Let's switch on B but not C, and let's finally switch on C but not B. Okay, so you can see that using logic.aly, both of these circuits indeed produce exactly the same output with exactly the same combinations of A, B and C. So now that we've seen that these two circuits are indeed logically equivalent, one of the questions you're probably asking is, why does this matter so much? Because we're going to be spending a lot of time simplifying Boolean expressions and using Carnot maps. Why do we actually need to bother? Well, let's pop up these two circuits again. We had our circuit which essentially was an illustration of our original Boolean expression, our original logic, and then we had a circuit which we produced or illustrated from our simplified logic. So if I was a manufacturer of digital circuitry for digital products, and I said to you, we've got a choice here, which one of these two circuits should I actually manufacture and put into my digital device? Which one of those two would you suggest? I strongly suspect you would say the one on the right hand side, simply because it is simpler and has less components, and you'd be absolutely right. All other things taken into account, the circuit on the right hand side is likely to be more cost effective to manufacture as a digital circuit solution. So let's wrap a little bit more formality around that, and we can say that a circuit on the right in comparison with the circuit on the left would be potentially more cost effective because There are less components to purchase, so there's less logic gates, less circuitry, and potentially we'd have a smaller printed circuit board as well, which would also save money in comparison to the one on the left hand side. We've got less components and circuitry, so that means the circuit on the right hand side may draw a little bit less power and produce less heat. So in that regard, these two circuits aren't likely to be too different, but certainly if you've got a very complex circuit design, excuse me, and in the process of using Boolean algebra or Karnaugh maps to reduce the complexity of your circuit, it might actually make a very big difference in things like cost and heat production as well. So all of these things are very, very important. Manufacturers will want to see a circuit design, or indeed other circuit designs as well, from which they can make an informed decision about which one is going to be the most cost-effective solution for their product. Okay, so just popping back to our original slide, excuse me guys, we said in this video we were going to explore the importance of being able to reduce a Boolean expression to a simpler form and to understand at a very high level actually the implications for real-world digital circuit manufacture. In this video we've seen that digital circuit designers and manufacturers will definitely want to determine the most cost-effective solution. They will want to make an informed choice for a circuit design. So being able to simplify an initial circuit design using Boolean algebra or Karnaugh map is actually very important in helping to determine what a cost-effective design looks like before committing to the manufacturing process. Okay, so that brings me to the end of this video. I hope that you found it useful. In the next videos, and of course in the classroom as well, we will be taking time out to learn the rules and theorems around Boolean algebra and then Karnaugh maps as well. I thought this would be a useful precursor before we actually jump in and do that. I will see you in the next video.